In this video, we're going to talk about the probability limits for ARMA forecasts. The reason this is important is we've been talking about forecasting and we have these formulas to calculate the forecast. But the question then is how confident are we that our estimate is accurate within a certain amount of certainty? And that's what these probability limits do for us. It's very similar to when you calculate the confidence intervals for the mean, for example. It's the same type of idea. So to get us started, let's review the forecast error term, which is given by E sub T naught of L. Remember the T naught of L notation. It's the same thing that it is for the forecast. That is, this is the forecast for L steps ahead where the forecast origin is T naught. And that's given by x of T naught plus L. So this is the actual value minus the predicted value, x hat T naught of L. So that makes sense that that's what we would call the forecast error. It's actual minus predicted. Now, we don't know what that value is going to be for sure, but we do know the expected value of it. The expected value of the error term is going to be 0. And we know the variance. The variance of the forecast error term is going to be sigma squared A times the sum from j equals 0 to L minus 1 of psi j squared. And you've seen that written in the text. Those are some properties of the forecast error term. And in addition, we know that these forecast error terms are going to be normal, if from normal. Now, hold on to those 4 facts for just a second, and let's remember something. It came up earlier in the book, and it's very likely come up very early on in your statistics training. Remember that if the random variable x is normal with mean mu and standard deviation sigma, we know that z equals x minus mu divided by sigma is distributed normally with a mean of 0 and a standard deviation 1, variance 1 as well. Well, we have the same thing going on here because we know that E of T naught of L is normal. We know the mean. We know the variance. So that means that we can write this as E of T naught of L minus its mean, which is 0, divide by its standard deviation, which is the square root of the variance, which gives us sigma A times the square root of this term. We know that that should be distributed normally with a mean of 0 and a standard deviation of 1, just like it is here. So that's very convenient. That's going to get us a long ways in this process. So here's what this says. If this line is true, let's just substitute what E of T naught of L stands for. That would then say that x of T naught plus L minus x hat of T naught of L divide by sigma A times the square root of j equals 0 to L minus 1 of psi j squared to the 1/2 should be distributed normally with a mean of 0 and a standard deviation of 1. And the next thing we'll do in this process is to recall that for standard normal random variable z, the probability that z lies within 2 standard deviations of its mean of 0 is about 95%. A little bit more technical than that, the probability that z is between negative 1.96 and positive 1.96 is 0.95. We're going to take that fact when I come back on the next light board and derive some more from there. Okay, let's continue where we left off. Recall that what we had said was that this term on the left side is really a random variable that is normally distributed with a mean of 0 and a standard deviation of 1. And so the good news about that is that we know from the standard normal table that the probability that a random variable that's normally distributed lies within 2 standard deviations of its mean is 95%. So that means we can write this as the probability that this big term here, x of t naught plus L minus x hat of t naught of L, divide by sigma A times the square root of j equals 0 to L minus 1 times psi j squared raised to the 1/2 less than 1.96 equals 0.95. And again, that's true because of the standard normal table. One other thing I want us to make sure that we're recognizing is that this is the actual value, this is the predicted value, and what we're trying to do is to see how close they are to one another. And what we're going to do at this point is we want to solve for this value because we're trying to get the probability limits, the confidence interval limits for the parameter. Okay, so we're just going to do algebra from here on out to solve for this to get it isolated and in the middle. So the next step would be then, let's multiply by this denominator on both sides. So that's going to look like negative 1.96 times sigma A times j equals 0 to L minus 1 of psi j squared raised to the 1/2 less than or equal to x t naught plus L minus x hat of t naught of L less than or equal to positive 1.96 times sigma A times